All right, so our first video that we'll look at, thank you guys for watching these, will be for section 2.3. We'll finish up what we were talking about in class last time with rates of change. This is our first kind of application section into applications of the derivative. We looked at velocity. We looked at that example with the height of a falling object falling off of a cliff, and found its instantaneous velocity at certain times, things like that. And then we started talking about marginals, marginal profit, marginal revenue, marginal cost, that kind of thing, our economics and business type application of derivatives. So we'll go ahead and continue on with another example of that. Just to remind you, we were talking about our demand function, which is an equation that relates the price of an object with the number of units that people are willing to buy and sell. And in particular, the way that we'll want it written, is as a function that gives us the price in terms of the number of units that we want to sell or the number of units that customers are willing to buy. So x in that equation there, this is our demand function, represents the number of units that we want to sell. And then p represents the price that customers are willing to pay in order to support that, that sales level. So the price that customers are willing to pay. I'll just write price there for that. And then once we've got that demand function, that equation or function relating the price to the number of units that we want to sell or that customers will be willing to buy, we can turn that into a revenue function and get revenue, R, equals the number of units sold times the price. And that, of course, will give us the total amount of revenue that we'll bring in from selling those X products at P dollars a piece, or whatever our units are in price there. So we've got a way of coming up with a revenue equation from one of these demand functions, from an equation that relates us the number of units sold and to the price of the object, from the idea of supply and demand. The higher the price, the fewer units that people will be willing to buy, the fewer units that we'll be willing to sell in that case. So let's look at this example of fast food hamburgers here. So this will be the demand function for a fast food restaurant's hamburgers. Oops. Clean that up a little bit. Okay. There we go. Fast food restaurants, hamburgers. And we'll say we're talking about maybe weekly sales at this particular fast food restaurant. So here it is. P equals 60,000 minus X divided by 20,000. An extra zero there, 20,000. I'm going to separate that out and we can see it a little easier. Or another way that we could write that, go ahead and divide both of those terms on the top by 20,000. Now we can't cancel just one of those, remember. We have to divide both terms on the top by 20,000 if we're going to do that. So 60,000 divided by 20,000 is 3 minus 1 over 20,000 times X. Okay? Now let's kind of take a closer look at that maybe. This P equals 3 minus 1 over 20,000 times X is the equation of a line, so we could graph this line and see what it looks like here. So let's say we want to, we'll graph it over here, but let's say we'll just find intercepts in order to do that. So the P intercept, you can think P of like Y, and then we'll find the y-intercept basically. So that would mean we want to plug in 0 for that x, and that gives us p equals 3, and then if we make that x 0, the rest of that just goes away. So our p-intercept would be 3. So let's go 1, 2, 3. That's $3 of price. What that really means is that customers would be willing to buy 0, x equals 0 hamburgers if the price for each of those hamburgers was $3. So their demand would go down to 0 at a price of $3. Okay, now let's find an x-intercept to go along with that. And so what does this represent? Well, this represents what would happen when the price is $0, when p equals 0. So what does that get us? 0 equals 3. Clean up that equal sign a little bit. 3 minus 1 over 20,000 times x. Sorry about the handwriting. I'm going to pick up the pen a little bit more. And we'll solve that for x. So we get 3 equals 1 over 20,000 x. I guess I move that 1 over 20,000 x over to the other side, but flip the signs there at the same time. And then we'll multiply by 20,000 and get 60,000 equals x. Okay, so there's our x-intercept. When p is 0, x equals 60,000, meaning if the price was free, in this case our customers would support buying 60,000 hamburgers, let's say weekly. Okay, and since that's a nice linear function, we have a straight line connecting those points. Now in reality those demand functions aren't always straight lines. If you study more economics, you might see some more complicated demand curves than that. But as you can see, if we increase the price going up on the y-axis here, then along that line our number of units sold would go down. If we decrease that price, then our number of units sold goes off to the right. As the price decreases, the number of units sold increases, and that makes sense with supply and demand. You'll always have a negative sloped line if we have a demand line for a product like that. What we want to do is take that demand function, we'll rewrite it on the next slide here in a little bit, and find the increase in revenue per hamburger for monthly sales of 20,000 hamburgers. In other words, find the marginal revenue when x equals 20,000. So find the increase in revenue per hamburger and what that really is the marginal revenue when we're at a sales level already of x equals 20,000 hamburgers. Okay. In other words, if we're at this production level of 20,000 hamburgers, we have our price set accordingly, according to that demand function. What's the marginal increase in revenue per hamburger at that sales level? So if we're producing 20,000 hamburgers, what's the revenue on the next hamburger is the idea there. Okay, and then we'll turn this into a marginal profit example here in just a little bit. So first, if we're looking for marginal revenue, then we need our revenue function. We need R equals, and what do we say that would be? Well, the number of units sold are X times the price. All right. Now I don't want to put in that 20,000 in for X just yet, because we want to find the marginal revenue, and we're going to need a derivative in order to do that. So I want to leave my variable in there. So what we will do is replace that P with our demand function that we saw in the previous slide there. So that was X times, and we'll go ahead and put in that P, and I'll do the second version of that. No, let's do the first version of that we had. The 60,000, the one with the fraction, minus X over 20,000. The other version of it, kind of in slope-intercept form, when we divide both terms by 20,000, gives us a nice way of visualizing that demand curve, or that demand line in this case. But for this purpose, it might be a little bit easier to go ahead and leave it as that fraction. We'll manipulate that just a little bit to help us out, though. Let's try to work on that just a little bit, like we said, because we're eventually going to want to take a derivative of this. It's not quite in a form where we can take the derivative yet, because we haven't seen how to take derivatives of two things that are multiplied like this, two functions that are multiplied. So I'd like to distribute that x through, but first maybe let's take care of this 20,000 on the bottom here. I'm going to go ahead and pull that out all the way to the front. Remember, constants work nicely in calculus. We can just leave them out front. So I'm going to pull out that over 20,000 out to the front as 1 over 20,000, and then we'll distribute that x through, and we'll get 60,000x minus x squared. Clean up those x's again. Okay, so hopefully you see what I've done there. We've taken that 20,000 and pulled it out front as 1 over 20,000, and then distributed our x through those parentheses on the top of that fraction that was inside, and we get 60,000x minus x squared inside. So now we're ready to find our marginal revenue, and marginal revenue is the derivative of our revenue function, so dr dx we called it. You could call it r prime if you like, but dr dx will be the symbol that I'll use most of the time for that. So think about taking that derivative. All right. That constant, what do we do with that constant? It stays out front, so 1 over 20,000 can hang around. And then we'll take the derivative of the rest of that in the parentheses using our derivative rules. So derivative of 60,000x using the power rule, that x turns into, the derivative of x is 1, as we've seen, so we get 60,000 hanging around, and the derivative of x is 1 times x to the 0, which is 1, minus derivative of x squared, bring the 2 down, and decrease that power by 1, x to the 1 is x. So we get 60,000 minus 2x. Alright, so now what we're ready to do is take that derivative and find our marginal revenue, our increase in revenue per hamburger when x is 20,000. All right, we didn't want to plug it in up here because that's just going to give us a constant revenue there for when x equals 20,000. We're trying to find how much that revenue is going to increase for the next hamburger, the marginal increase in revenue per hamburger at that sales level of 20,000 hamburgers. So first we take the derivative to get to here, and now we can plug in that x equals 20,000 and get our marginal revenue. All right, so marginal revenue. When x is 20,000, we get 1 over 20,000, plugging in for this x here, 60,000 minus 2 times 20,000. All right, and we'll go ahead and evaluate that. Let's see, 60,000 minus 2 times 20,000, it's 1 over 20,000 times 60,000 minus 40,000 will be 20,000. And we get a marginal increase in revenue then of $1. $1 per hamburger is our marginal revenue at that certain sales level of 20,000. Really what I think that means is that's our price per hamburger at that point, just from that price function. But we've done this now in terms of marginal revenue and found that marginal increase then. All right. So what we'll do now is take that one step further. Take a pause here if you want and look over that example one more time. But we'll take that one step further and turn it into a marginal profit example. Okay, so let me clear this out. Go ahead and pause it there if you like and look through that one more time. All right. And we'll turn this into a marginal profit example now. Okay, which is really probably something that's more useful to that fast food chain. They don't care how much their next hamburger is going to bring them in revenue. They care how much it's going to bring them in profit, because that next hamburger also costs them a little bit to make, and so that revenue isn't all profit at that point. So let's add in a cost function then. So we'll suppose that the cost for this fast food restaurant, the cost of producing X hamburgers is given by this function. C for cost equals 5,000 plus 0.56x. Okay. In other words, what I think we're saying here is that their kind of baseline cost is $5,000 for overhead and paying employees and things like that, and maintenance on equipment and everything, plus 56 cents per hamburger is the idea there. That's the maybe ingredient cost and the cost for the employees' time that are making those hamburgers. Okay. So there's our cost function. What we'd like to do is find the profit function. And what we'll do is use this profit function to determine the profit and the marginal profit, so the profit on the next hamburger, when at three different sales levels, so 20,000, 24,400, and we'll see why we picked that number in a little bit, and 30,000. So let's say find the profit and marginal profit at three sales levels. At 20,000 hamburgers, so when x equals 20,000, 24,000, 24,400, excuse me. Again, a weird number, but you'll see why we picked that in a little bit. And 30,000. Okay, so how are we going to find a profit function? Well, we wrote this down last time. Profit is the company's revenue, in this case the fast food restaurant's revenue, from those hamburgers minus the cost of producing those hamburgers. Okay, so we'll take our revenue function that we had on the previous slide. Let's use that one with the constant out front. 1 over 20,000 times 60,000 x minus x squared. I was taking that price, that demand function, and then multiplying it by the x. And then we need to subtract that cost function. So minus, and use some parentheses here when we subtract, because the whole cost function needs to get subtracted. And our cost function from the example of above is 5,000 minus 0.56x. Okay. Now, it may be nice if we could go ahead and combine like terms there a little bit and make that look a little bit nicer. So let's see, we'll go ahead and distribute through 1 over 20,000 times 60,000x, 60,000 on top, 20,000 on the bottom gives us 3, and then the x is hanging around on top. 3x minus 1 over 20,000 times x squared. Okay, then we've got to distribute that negative through as well. Minus 5,000 plus 0.56x. Okay. Then we can combine like terms. Let's see, collect the x terms maybe, and then we'll put those in the order that we're used to, with x squared out front, then the x's, then our constant terms, and we'll get our profit function. P equals, let's see, let's keep that x squared term out there first, negative 1 over 20,000 x squared plus 3.56x, combining those x terms, and then minus our constant there, minus 5,000. Okay, and that minus 5,000 there, of course, meaning, oh, what happened there? Let's fix that a little bit. Sorry about that. We had c equals 5,000 plus 0.56x. Somehow I switched that to a minus there. So let's see. Minus that positive 0.56x should give us negative 0.56x then. Clean that up. And that'll change our number here. Sorry about that. I'm not going to start over a new video at this point. So then we have 3 minus 0.56, and that gives us 2.44 on our x term there. Okay. Sorry about that. You guys are probably yelling at the screen during that if you saw me slip up and put that that negative sign there. So I think that fixes it for us and gets us to where we want. Okay, so this answers the first part of our question. We found the profit function. We've got that part taken care of. Now we want to find the profit and the, terrible handwriting again, marginal profit at these three different sales levels. 20,000 hamburgers, 24,400, and then 30,000 hamburgers. So let's go to a new slide here and we'll do that. We'll find our profit. We've got our equation for profit right there. And then we need to take the derivative to find marginal profit. So let's go ahead and do that on the next slide. Okay, so here's, I'll go ahead and rewrite that profit function. So we have it up at the top here. Negative 1 over 20,000 x squared plus 2.44x minus 5,000. Okay, so that's the company's profit. If we're selling X hamburgers at that sales level of X hamburgers, we can plug in an X and find the profit at that point. And then we want to find the marginal profit. So marginal profit is our derivative of our profit function, just like we did marginal revenue a little bit ago. So we'll go ahead and take that derivative, and let's see what we get. Negative 1 over 20,000 times the derivative of x squared, which is 2x. So we'll bring the 2 down. Keep that constant up front. Derivative of x squared is 2x. Bring the 2 down and reduce that power by 1, but x to the 1 is just x. Plus 2.44. That constant hangs around, and the derivative of x is 1. And then the derivative of a constant without any x's attached to it is 0. So that part, that piece doesn't contribute anything to our marginal profit function there. Okay, after we take that derivative, it's 0. So let's see. On this first term, we've got 2 over 20,000. That's negative 1 over 10,000. Oops. 10,000. X plus 2.44. Okay. Now, what I'd like you to keep in mind as we start plugging in these numbers is that this profit function is a quadratic function. It's got x squared in it. So its graph should be a parabola. Think back to algebra and think about which way that parabola should open. And if you're looking at this first term here, that a on the x squared term, that constant on the x squared term is negative. So that should be a downward opening parabola there. Okay, meaning as our sales level goes up, our profit will start to increase, and then we'll reach some maximum profit, and then eventually those costs start overtaking things. As we want to increase our sales, we have to start reducing the price also, and then our profit starts going down. So on this side, we've got kind of increasing profits, and then at some point we reach kind of a maximum profit level, and then the profit starts decreasing. So think about that graph there. Sorry about the sloppiness on that part. I'm just going to clear this out. I just want you to think about that parabola, though, downward facing parabola. Since we've got an x squared on our profit function with a negative coefficient on it. And on the left side over here, we've got increasing profit as x starts to get bigger. As our number of units sold starts to get bigger, then at some point we reach a maximum profit, and then that profit starts declining. Again, maybe those costs are getting too big, or maybe our price has to start decreasing in order to support that level of sales, as we saw from the demand function originally there. So let's go ahead and plug in those 3 numbers that we were asked to. We'll do kind of a 3-column table here. We'll say here's our sales. Here's our profit at that sales level, and then here's our marginal profit. Okay. Don't like that touchscreen today. It's okay though. Profit. All right. So the 3 numbers we were asked to plug in were sales of 20,000 hamburgers first. That's plugging that in for our x. And we'll plug that in for p, and I'll write this one out, but then eventually we'll just start plugging it into the calculator. Negative 1 over 20,000. Plug that into our p equation here for profit. Plugging it in for the x times 20,000 squared. Plus 2.44 times 20,000. Minus 5,000. Okay, let's see. I'm going to plug that into the calculator here. 20,000 squared, and then divide it by negative 20,000, let's say. Okay, that gets me negative 20,000 overall for that first term. Plus 2.44 times 20,000 minus 5,000. and I'm getting a profit of $23,800. Oops. $23,800. Okay, and we'll take that same x equals 20,000 and plug it into our marginal profit function, the dpdx. I'm going to use this version of it. We'll plug in that 20,000 for the x and see what we get there. So I'm going to again write this one down, but eventually we'll just type it into the calculator for the next ones. Negative 1 over 10,000 times 20,000 plugged in for the x, plus 2.44. And we get, type that in there, 0.44. Yeah. 0.44. That's dollars, so that's 44 cents profit per unit. So when we're at that production level, or at that sales level of 20,000 hamburgers, the next hamburger we'll make 44 cents off of. Remember, what was our marginal revenue on that? Marginal revenue at 20,000 was $1. And then from our cost function there, we could see that it costs 56 cents per hamburger to make those. So that's that $1 minus the 56 cents there, giving us the 44 cents per unit at that production level. The nice thing about this marginal profit equation, though, the derivative of our profit function, is that we can then plug in several different values and don't have to worry about going back and finding the marginal revenue every time. We already found the marginal revenue for this sales level, but we haven't found it for the next two. So now that we've got this profit and this marginal profit equation from revenue minus cost, and then taking the derivative of that profit function, we can plug in the other two numbers much easier. All right, so up our sales to 24,400. And again, you'll see why this weird number shows up here in just a little bit. And I'm not going to write all that out again, but plugging it in where we plugged in the 20,000 before, in for those x's in our profit function. For that one, you get 24,768. Go ahead and type that in, double check me there, but I think that's what you get. 24,768. Okay, so we've increased our profit by increasing our sales level from 20,000 to 24,400, increasing by 4,000, 4,500 or so. 24,768 we have. Okay, that's a 7 there, sorry. Okay. All right, we'll do the same thing in our marginal profit function and see what that marginal profit looks like at that point. So once we're at this sales level of 24,400 hamburgers, how much do we make on the next hamburger? So let's see, plug that in for the x in our marginal profit equation there. Get negative 1 over 10,000 times 24,400 plus 2.44. I think in this piece you get negative 2.44 plus 2.44, and we get a marginal profit of $0 per hamburger. All right. In other words, once we're producing 24,400 hamburgers, the next hamburger we make a marginal profit of 0. So would we want to sell that next hamburger? No, it's not really worth it to sell that next hamburger at that point. Once we're at that sales level, where that's coming from, I think, is again the cost of producing that next hamburger isn't going to well, it's going to be more than the revenue that we'll get from producing that next hamburger, because I think at that point we'd have to reduce our price to support that level of sales. So the customer support for sales level of 24,400 would require us to reduce that price to get our sales up to that level. We wouldn't be able to make any marginal profit on the next hamburger there. So what I think this means is that we're at the top of this parabola here. If you notice at the top of that parabola what the tangent line would look like, it would be a horizontal line, and horizontal lines have a slope of 0. And if you remember, slope is the same thing as the derivative. So the slope of our curve here is given by this dpdx that we found, the marginal profit. So when we get to that marginal profit of 0, that means that we're at the top of that parabola there. And I think we've reached our maximum profit at that point. All right, now just to see that, let's increase our sales a little bit more. Again, to do that, we'd have to decrease the price and see what happens if we up that to, what was it, 30,000 we were asked for. So we'll give that one a try and see what that looks like. So I think that 20,000 maybe over here, where we're on the upside of profit there. We still make more profit by selling the next hamburger at that point. And then once we get to our 24,400, we kind of reach that maximum profit. And then let's see what happens if we increase that even more to x equals 30,000 in sales. Plug in that 30,000 into our profit function, again into our first equation up here, in for the x, and we get 23,200. You might notice something about that there, comparing it to the other two. It's less than our profit at 24,400, because I think what's happening here is that we're on the downside of this. Again, at that sales of 30,000 hamburgers, we may have to reduce the price too much to support that that cost. In fact, I think if you look back at that graph that we drew, no, that's not quite where that was. 60,000 was what we have to do to get them for free. But let's go ahead and put in the rest of that then. So our marginal profit, go ahead and plug in that 30,000 into our x in our marginal profit equation, and you get -3 plus 2.44, and that gets you a marginal profit of -56 cents per unit. Let's put that negative out front, that makes more sense. My units would be dollars there, 0.56 let's say, but that turns out to be negative. Again, I think we're on the right side of this parabola here, and our marginal profit is negative because we're on the downward side of that slope, where the slopes would be negative there. So we get a negative marginal profit, meaning we definitely wouldn't want to increase our sales from that point, because we were losing money at that point by making any more hamburgers there. Once we get past this marginal profit of 0, then we're on the downside. We would not want to increase our sales anymore. We'd want to keep it at this level of 24,400 hamburgers, again, maybe weekly sales or something like that, to be at this maximum production level, maximum profit up here on top of our parabola, looking at the graph there. Let's see. We've got this idea of a maximum profit, I think, from this 0 marginal profit. That's kind of our goal in order to maximize profit, as we'll see as we move forward into chapter 3, is going to be to find where we have a horizontal tangent line, where our slope is 0, and that'll be where our marginal profit is 0, and that'll correspond to this maximum profit that we're seeing. Now, you don't really see the maximum profit from just these 3 numbers here, but hopefully that picture kind of helps you see what's going on there. When we're at this 24,400, we've reached this maximum profit level here of $24,768. Okay. Now, what else might this company be interested in? Okay, so once they found this maximum profit, they want to know how much should they charge for their hamburgers at that point in order to achieve that maximum profit. So how could we do that? Well, to find the price in order to support that sales level, we could go back to that demand function and plug in 24,400. So we could go back. Let's see, that was right here. Into our demand function, where P was solved for in terms of X, plug in that 24,400 and see what price we should charge in order to get that sales number of 24,400, and thus get our maximum profit of whatever it ended up being, 24,768. And I think when you plug that in, if you like, plug in 24,400 for the X, you find that the company should charge, or that restaurant should charge $1.78 for each hamburger in order to get that sales level of 24,400 to maximize the profit. So there's a lot of little applications like that we can do, but it all boils down to one little piece of the calculus there, was taking the derivative to find that marginal profit, or previously taking the derivative to find marginal revenue from our revenue, and then we can apply all that to get things like the maximum profit for that company, which we see is achieved here at a sales level of 24,400 hamburgers. All right, so take a look back through that example if you like. There's similar examples in the book as well, and then work through the homework there in section 2.3. That's our first big application of derivatives. You see that the only place where we really use that new calculus part is in finding that marginal profit or marginal revenue function, taking the derivative of our profit or revenue function to get that marginal profit or marginal revenue function as we did earlier. And the rest of it is mostly algebra, manipulating those functions to get them to look how you want. So we did plenty of distributing and things like that, and then plugging in numbers to see what happens at certain different levels. Eventually in chapter 3 we'll be interested in finding these levels that maximize profit, or maybe something like minimize cost and things like that. So we'll be interested in finding these zero marginal values here to figure out maximum or minimum levels when we when we can find those at least. All right, so work through the homework. Let me know if you have questions on those, and then I'll post another video for the next section in just a little bit here.